All right, let's get right into it. To make sense of the universe, we humans, well, we tell stories. We test them out, we keep the ones that work, and we toss the ones that don't. But the deeper we look, the stranger these stories get. And today, we're diving into one of the absolute strangest of them all, string theory.
I mean, this is the big one, isn't it? It's the question that keeps physicists up at night. It's this deep, deep quest to figure out the fundamental rules, the basic building blocks of, well, everything we see and everything we don't.
And yeah, that quote, it just nails our topic today. String theory is this huge, sweeping story that gives a totally radical new answer to that ultimate question. But to even understand why we needed a new story in the first place, we have to start with a much, much smaller problem.
So our journey starts by zooming in. And I mean way in. We're going past the molecules, past the atoms, all the way down to the elementary particles themselves. And it's right here, at the very bedrock of reality, that things start to get really, really weird.
Okay, so first, a super quick refresher on how you see anything at all. A wave of light zips along, it hits an object, bounces off, and carries information about that object straight to your eyes. The key thing to get here is that seeing isn't passive. It's an active process. To see something, it's to literally interact with it, to touch it with light.
And right there, that simple fact creates a massive problem when you get down to the quantum level. See, for a big object like a baseball, the light hitting it doesn't really matter. But particles, they're so incredibly tiny that the very act of hitting them with a wave of light that's energetic enough to see them actually changes them. It's kind of like trying to find out a balloon's exact location by throwing a bowling ball at it. The moment you find it, whoops, it's not there anymore.
Now, this isn't because our tools aren't good enough. No. This is a fundamental rule of the universe. It's called Heisenberg's uncertainty principle, and it basically means there's a built-in fuzziness to reality at these tiny scales. We can know where a particle is, or we can know where it's going, but we can never, ever know both with perfect accuracy at the same time. Which leads us to this really mind-bending question. If we can't ever truly see one properly, if just looking at it changes what we're looking at, then what is a particle? What is it really? And the honest answer? We don't actually know.
So, what did physicists do? They did what people do best. They came up with a new story, a brilliant, super useful fiction. They just decided to pretend that a particle, like an electron, is a perfect, zero-dimensional point in space.
And this idea was a total game changer. By treating an electron as just a simple point with a couple of key properties, like mass and charge, physicists could finally build equations that predicted how it would behave. This story, which we call quantum field theory, became the foundation for the whole standard model of particle physics.
So how well does this little story actually work? Well, it's just unbelievable. The predictions made by this point particle idea match what we see in experiments with a margin of error that is, get this, 0.00000000000002%. It is one of the most successful scientific theories ever created. But there was one massive, glaring problem. And that problem is gravity. The biggest, most obvious force we experience every single day just completely refuses to play by the quantum rules. Our amazing, incredibly successful story about particles had no chapter for gravity at all.
And this table really shows the conflict perfectly. Think of the universe as a play, right? Quantum physics, that's the story of all the particles and how they interact. Those are the actors. But Einstein's theory of general relativity, that describes gravity as the very fabric of space-time itself. That's the stage the actors perform on. And here's the problem. The story of the actors and the story of the stage speak completely different languages.
So naturally, physicists tried to jam gravity into the quantum story. They tried to invent a particle for gravity, a graviton. But every single time they tried to write the math for it, using that point particle idea, the whole thing just collapsed. The math broke. It would spit out nonsense answers like infinities. The two stories were just fundamentally incompatible.
So, we needed a new story, a deeper story, something that could unite the actors and the stage. And this meant we had to rethink the very first assumption we made. What if a particle isn't a point after all?
It's such a simple question, right? But the answer changes everything. What is the very next step up in complexity from a zero-dimensional point?
A one-dimensional line, or as the theory calls it, a tiny, vibrating string. This is the absolute heart of string theory. The idea that the fundamental building blocks of reality aren't points, but these unimaginably small, vibrating filaments of energy.
And this is where the idea becomes truly elegant. Think about it. A single violin string can make lots of different musical notes just by vibrating in different ways. Well, in the same way, a single fundamental string can look like many different particles. If it vibrates one way, we see an electron. If it vibrates another way, we see a quark. And, this is the crucial part, another very specific vibration pattern has the exact properties of the graviton, the missing gravity particle. In one beautiful idea, all the particles just become different notes in this grand cosmic symphony. Now, this was just a breathtaking idea. For a while, it really seemed like this could be it, the theory of everything. But as physicists dug into the math, they found out that this beautiful story came with some very, very strange requirements. The first huge hurdle is this. For the equations of string theory to actually work and not fall apart, the universe can't just have the 3 dimensions of space and 1 of time that we all know and love. No, it needs 10. And yeah, that leads to the obvious question, right? We experience 4 dimensions, so if there are 10, where in the world are the other 6? Well, the leading idea is that they're curled up incredibly, incredibly small at every single point in space. Way too tiny for us to ever notice, but, that's just an idea. It's not evidence.
And this is maybe the biggest problem of all. Science works by making predictions that you can test and then doing experiments to see if you're right. So far, string theory hasn't given us a single prediction that we can actually go out and test. So, if we can't prove it, what good is it?
This is where we kind of need to change our perspective a little bit. Maybe the goal of string theory isn't to be the final, capital T, truth, but to be a really powerful tool that helps us ask better questions. Okay, imagine you want to build a giant cruise ship, but all you have are the blueprints for a tiny little rowboat. They're obviously very different. But by studying those rowboat plans, you can learn fundamental things about buoyancy, about how things float, stuff that will be absolutely essential when you go to build the big ship. In the same way, physicists use the math of string theory as a kind of toy model to explore how quantum gravity might work, learning really valuable lessons, even if the theory itself isn't the final story.
And that brings us right back to where we started. String theory might not be the story of everything, but just like that mathematical fiction of the point particle turned out to be one of the most useful stories in the history of science, the story of strings is proving to be an incredibly valuable tool. It's helping us discover new kinds of math and explore what a theory of everything could even look like. So maybe the final question isn't just, is it true, but where will this story lead us next?